So, welcome you all in my next lecture. Now, this lecture I will talk about, of course, the notions of vector line integral I discussed in my last lecture, and then of course, I talked about kind of simple closed curve or simple closed contour, and then of course, I just defined the notions of vector line integrals. Now, today my plan is to talk about bit of properties of vector line integral, and on top of that I will calculate some of the examples and some applications. So, that is my plan for today's lecture. But before that, in my last lecture I was talking about if I have a curve, then there is a notion of what is called negative of this curve. And if I have a curve with the kind of given orientations, so negative of this curve, it traced out same set of points, but the directions will be reversed compared to the given one. Okay. So, maybe there I will give just one example that if C has a say anti-clockwise directions, then minus C will have a clockwise directions. In my last class you can remember, so I was bit confused talking about whether if C has a direction some say clockwise or anti-clockwise, minus C will have the opposite direction. Maybe I will start again recall that one, just I will just convince you yes this is the case, and then I will go to the what is called properties of vector line integral and some couple of examples. Now, so as I said, so what is, so suppose opposite curve, right. So, if C has a C is the given curve with the parameterization say R of t, then minus C, as I said, it traced out the same set of points, but it will be in the reverse order. Okay. So, one example, look at this example. Suppose C is RT 2 cosine t 2 sin t, that means it is a circle of radius 2. So, that means you just write it, it is a circle of radius 2. Now, if t is equal to 0, then what point we will have? You will have this point, that means 2 comma 0. And if t is equal to pi by 2, if I just check, so cos 90, that means it will be 0, sin 90 is 1, that means it is 0 comma 2. So, that means it is actually moving in this direction. So, that is the natural orientations with these parameterizations. Now, if I look at the minus of C, so same curve will be there, it traced out the same set of points, that means that again it is a circle of radius 2. Now, look, so what is my parameterizations? R of t, which is 2 cosine t minus 2 sin t, perfectly all right because of these definitions, R of minus t. Now, this time t varies from minus 2 pi to 0. Now, at t is equal to minus 2 pi, so at t is equal to minus 2 pi, you just evaluate. So, this should be what? So, that means this should be 2 times cos of minus 2 pi, comma minus 2 sin of minus 2 pi, right. Okay. So, what is this point? So, this point you just calculate it because cos of minus theta is equal to cosine of theta. So, that means this should be 2 cos 2 pi as it is, and sine of minus theta is minus sin theta. So, minus minus get cancelled, this should be, that means 2 sine of 2 pi, but cos of 2 pi is 1, okay, and sine is 0. So, therefore, actually this will give you the point 2 comma 0. So, therefore, I am having this point. Now, what I will do, I am saying that minus C will be in the clockwise direction. So, now look at the points t is equal to what is called minus 3 pi by 2. Okay. So, t is equal to minus 2 pi, you will have this point, not an issue, or this point 2 comma 0. Now, I am considering the point t is equal to minus 3 pi by 2. Then put the value here, then what we will have? You will have 2 times cosine of minus 3 pi by 2, comma minus 2 sine of minus 3 pi by 2. Okay. And what is this? You just, so that means this is 2 cosine of 3 pi by 2, comma, so minus sine of minus theta is minus sin theta. So, 2 sine 3 pi by 2. Then what will happen? So, you just write it cosine of pi plus pi by 2, then 2 sine pi plus pi by 2. Okay. You just use the trigonometric formula. So, this should be what? So, all sin tan, so that means pi plus, so that means 2 cosine of pi by 2, comma minus 2 sine of pi by 2. And what is this? That means 0 comma minus 2. So, then what point? So, that means this is the point, 0 comma minus 2. So, that means actually for the negative of this curve, actually it is moving in this direction, that means clockwise directions. So, therefore, if C has a directions, the natural direction, natural orientations, minus C will have the opposite one, that they traced out the same set of points, that is perfectly all right, but the directions will reverse. If C has one directions, minus C will have the opposite directions. Okay. So, now I think it is clear. Okay. So, these are the things I have discussed. So, direction and orientation. So, like if I have a curve simple closed, what is I have written. So, if suppose if parameterized by say r of t, so then that kind of things you can also visualize in this way. If C is parameterized, so that the interior bounded domain, that means if I have this say what is called simple closed contour C, and if I moving in this direction, so this is the interior bounded domain. So, I will move along C in such a way, so that in my left hand side always have the interior bounded domain, then I am actually the directions I am talking about is called anti-clockwise. This is anti-clockwise or counter-clockwise or positive directions. Now, instead of that, if I am moving in this direction, so that means this time what will happen, in my right hand side it will have the interior bounded domain. So, that direction I am saying as a negative direction, so clockwise direction, that I already discussed. Okay, fine. Then vector line integrals, of course, these are the things, simple closed curve C, if it is positively oriented, minus is negatively oriented, and always remember, if the orientation is not given for a given simple closed curve C, okay, suppose it is not given, you assume that, or by default I am talking about that my simple closed curve is actually oriented positively. Okay, so now the definitions of vector line integral I already said. So, now this time what we will have? This time now compared to the scalar line integral, I will have a vector field, okay. I will have a simple closed contour, okay. Then I am taking the partitions of my simple closed contour. How to take the partitions? If I have a simple closed contour, the corresponding parameterization is there. You take the partitions of your interval a to b, then it will give you a parameterization of your simple closed contour by finitely many subarcs, let it be Ci. Then what you do, take a point Pi star, I have written Pi star from the subarc Ci. Then you just, what you have to do, you have to make a Riemann sum. What you have to do? So, first you just take the, since you are starting with a vector field capital F with some domain D subset of Rn, and your domain contains your simple closed contour C. So, therefore, since Pi star is a point in C, so therefore, capital F acting on Pi star, it is the corresponding vector associated at that point Pi star. And then what you do, since it is simple closed contour, that means that there is a concept called tangent vector that I am denoting as T of Pi star. What you have to do, you just take the dot product or take the inner product. So, that will give you a scalar. Then you have to take what is called arc length of your Ci, then you have to sum it up I from 1 up to n if you have n many points in the partitions, and then take finer and finer partitions, that means norm of the partition goes to 0. If the limit exists, then I am saying that this is called the what is called vector line integral. Okay. So, as I said, this is the arc length, this is the unit tangent vector, and F, capital F of Pi star, which is nothing but the vector associated at the point Pi star, because capital F is a vector field. Once I have that one, so this I have talked about vector line integral of F over the directed curve C, which is nothing but the right hand side, to consider the Riemann sum. I just said how to make it Riemann sums. If norm of the partition, that means I am taking the arc length is very small, then if the limit exists, then this is the corresponding notations, this integration over C capital F dr. But it is very important to note that we may write the vector line integral over the directed curve C as this one. Now, what is the look at the right hand side? See, left hand side is the vector line integral of capital F over C, right? And what is the right hand side? See, right hand side is nothing but the scalar line integral, right? And what is my integrand this time? Actually, integrand this time T, what is the map is actually RT. So, that means RT is an element in C, right? So, this goes to what is called capital F of RT. That means this is the corresponding vector associated at the point RT, and then you will have the corresponding tangent vector at the point RT. Okay. So, this is the dot product. So, this is the corresponding scalar field, though this is the corresponding scalar field. It is a map from C, which is of course subset of Rn. So, RT goes to this map. This is a scalar, right? This is belongs to R. So, that means if I integrate this scalar field, or that means if I take the scalar line integral of this function, this will be nothing but the vector line integral of my capital F. Okay. So, therefore, if I have a vector field, if I have a simple closed contour, if I have a domain of my vector field contain the simple closed contour, then the way I have defined the definitions of vector line integral, which is nothing but the scalar line integral of the scalar field, this is the functions RT goes to this one, and make the scalar line integral. Okay. This clearly follows from the definitions. Okay. So, now couple of observations. So, vector line integrals and scalar line integrals, I just said, I have written more explicitly. What is that? Okay, suppose C is a piecewise smooth curve, and suppose it has a parameterization capital R. Since it is smooth, so therefore R prime T is non-zero. In other words, norm of R prime T is non-zero. So, once it is R prime T is non-zero, so therefore I can talk about at the point RT with the unit tangent vector. So, at the point RT on my simple what is called piecewise smooth curve at RT, the corresponding tangent vector I am denoting as T of RT, and which is nothing but R prime T divided by norm of R prime T 2C at the point RT. And what is this? I am just saying that F dot T, that means it is a dot product, okay, because this is a vector, this is a vector. So, F dot T is nothing but the tangential component of my vector field capital F, number 1. Number 2, the corresponding vector line integral of capital F over C, which is nothing but that corresponding vector associated at the point RT, because capital F is a vector field, times what we have to do, the corresponding the what is called tangent vector, that is R prime of T, this is the dot product, and then dt. So, this is the formula, and then I am writing in terms of unit tangent vector, then means capital F of RT times T of RT, then one this factor will come out, because your T of RT is nothing but R prime T divided by norm of R prime T, and which I am writing as F dot T ds, or which is same as this is the scalar line integral of this scalar field F dot or F inner product T. So, therefore, that is the conclusion I have written. Vector line integral of capital F is nothing but the scalar line integral of the dot product F dot T. So, that means if I consider this scalar field, that means the map RT, which is element in C, to F of RT, okay, and then dot product with T of RT, okay. So, this is the one. So, this is the dot product unit tangent vector, this is the scalar field if I integrate. So, this is nothing but the corresponding what is called scalar line integral of this scalar field is nothing but the vector line integral of capital F. So, this is important, because when I will talk about some examples, say okay, calculate this is the vector field capital F, and this is the what is called smooth piecewise smooth curve, okay, or contour. So, you just calculate what is the corresponding vector line integral. So, that means you have to get the parameterizations of your piecewise smooth contour or curve, and then you have to just use the formula, and these are the formulas which are useful to calculate those vector line integral. Okay, so this is couple of notations of vector line integrals, because various books uses various notations. Now, when C is closed, okay, that means your if it starts from say initial point R of A and in the final point is R of B, if C is closed means R of A is exactly equal to R of B, then the line integral, the integration of capital F over C dr. So, this is the kind of notation, that means you will have this circle, that means actually I am talking about what is called when my contour C is closed actually, okay, simple closed contour, smooth. Okay, so that is one of the notations. For R2, that means 2 dimensional Euclidean space, if I have capital F vector field as 2 components, say capital P comma capital Q, then the line integral is written as this is the vector line integral of capital F over C, which is nothing but that integration over C P dx plus Q dy, and for n is equal to 3, it will have 3 components P, Q and S. So, the corresponding vector line integral, this is the corresponding notations. So, these are the notations kind of various books follows in this way, okay. Fine. So, now let me see couple of examples, then it will be more clear. For example, I want to calculate that this vector line integral capital F over C, and what is my C? So, C has a parameterization, so I have written, so it is a parameterization. So, T comma T square or T running from 0 to 1. So, I then C is a curve in R3, and this is my corresponding vector field functions capital F from R3 to R3 x comma y comma z, it goes to xy comma yz comma zx, okay. So, now what is the formula? Integration over C of capital F dr, which is nothing but look at this formula. So, as I said, so this is the formula, okay. So, you have to just do capital F of RT, RT is given parameterization, dot you have to take the dot product and you have to just integrate. Okay, what is capital F of RT? So, of course, here F is given, so therefore, what is capital F of RT, which is nothing but you just do it. So, that means capital F of RT, so that means T square, that means x comma y, that means I think this should be what? This should be x times y, that means TQ first component, YZ, that means T4, and then what about Zx, that means again TQ. Dot product with R prime T means 1 2T comma 2T. What is the dot product? It means TQ plus 2T5 plus 2T4, TQT, so 2T4, and which is nothing but this one. Then dt you just calculate it, it's very simple integration. What it turns out that it should be, the value will be 59 by 60. Okay. This is first example. Another example, it says that okay, calculate this. You see, this is the different notation I am using, right, the earlier one. Okay, so if I go back, so this is this kind of notation. So this is nothing but I am talking about if capital F has two components p comma q. So this is the vector line integral I am talking about. If the right hand side has p q s and dx dy dz, that means actually I am talking about this vector line integral. So once I have this one, so that means this is my p, this is my q. What is my vector field? Capital F is equal to p comma q, that's a two component, and what is my c is the line segment from 0 comma 2 to 1 comma 4. So you can just have the parameterization. So what is my parameterization? 1 minus t times 0 comma 2 plus t times 1 comma 4. If I add it, what will happen? So this should be t and this is 2 minus 2t plus 4t. So that means 2 plus 2t. So that's the parameterizations, right? So this is my parameterizations. So this is the vector line integral. That means what is my capital F? My capital F is nothing but actually y comma x square and then sine pi y. Okay. So this is my vector field. So that means you just have the parameterizations f of r t you just do, then dot r prime t. So if I do that, then what it turns out is that this is nothing but this is the corresponding, you just calculate it, it's very easy because you will have the f, you will have the r t, f of, so that means what you have to do, f of r t dot r prime t. Now r prime t you can have 1, what is r prime t? This is 1 comma 2. So this is the r prime t, right? And what about f of r t? R t is no t comma 2 plus t. You just do some little calculations. What it will give is that this is the f of r t dot product with r prime t, which is nothing but this one, and you have to just integrate with respect to t variable. So if that means if you do that, then this one will come. Anyhow, you just do it, then you'll be able to get it, and the value will be 7/6. Okay. So I hope it is clear. In fact, if you want, maybe I'm calculating it. Okay, what is capital F of r t? Then it will be clear. So capital F of r t, what is capital F? This is y x square sin pi y. So that means x square y. So that means this should be 2 plus 2t times x square, that means t square. Okay, comma sin pi y, that means 2 plus 2t. So that means, and then r prime t, that means this should be 1 comma 2. If I take the dot product, then what will happen? So that means 2 plus 2t times t square, that is one integration, that means this is the 1 plus 2 times sin what is called pi of 2 plus 2t dt, and that is the second one. Okay. So you can easily get it. So these two example, very simple example, but with the different notations, right? Vector line integral I just explained. Okay. So couple of important notes, that is like in the scalar line integral I have discussed. So first one is that in the vector line integral, integration over c f dr, the integrand functions capital F is vector valued because I am starting with a vector valued or vector field, okay, and hence this line integral is called the vector line integral. As I said, I already said this times. So for the scalar line integral, I am starting with a scalar field, and for the vector line integral, I am starting with a vector field, and domain contains corresponding smooth piecewise curve C. Okay. And note that the integration is along or directed or oriented curve C. This time I am taking actually curve C with a parameterization T, and it will have a usual orientations. Okay. Second one, the vector line integral, this one can be informally, well, this is informally described as the, well, as I said, as the scalar integral over the curve C of the tangential component of capital F in the direction of C, because I am actually taking the vector. Since capital is a vector field, so I am taking the vector associated at the point r t, and then I am taking the tangent at the point r t, and then I am taking the dot product. So sometimes informally it says that as the scalar line integral on C of the tangential component, because I am taking the dot product with the tangent vector, that is called tangential component of F in the direction C. So that is informally one can say. What about the third one? The value of this integral, that is vector line integral, is always a scalar. Of course, it is nothing but the scalar line integral of this inner product, na, f dot t. So it will give you a scalar. So therefore, the value of this vector line integral, it's always a scalar, because this is the dot product. Of course, this should be bold, I think. Okay, this should be bold, f dot t. Okay, bullet. Okay, so that f dot t is a scalar valued, and this is nothing but this vector line integral of capital F, which is nothing but the scalar line integral of f dot t over C. So therefore, this gives a scalar. Another one, so this time is important. So it is important to note that the orientation, this time orientations or directions of curve has some effect, unlike in the scalar line integral. So it is important to note that the orientation or directions of the curve C does affect. In the scalar line integral, it does not affect, but in the vector line integral, it does affect. Okay, so does affect the value of the vector line integral. For example, if minus C of course, if C has a natural orientation, minus C will have a opposite orientation. So, if minus C is the opposite curve of the directed curve C, then the corresponding vector line integral of capital F over C, which is nothing but the vector line integral of capital F of the negative curve minus C, but this time you will have to hit it with minus 1, or you can write integration minus C f dr, which is nothing but minus of integration C f dr. Okay. So, there will be minus signs. So, integration over minus C f dr is nothing but minus of integration over C f dr. Okay. There is a minus sign will be there. Now, similarly, so because as I said, it is nothing but the like this one, like the scalar line integral on C is nothing but a tangential component of f in the direction C. So, then you can say that similarly one can define a vector line integral of capital F by taking the dot product of f at the point r t with a unit normal vector. Now, this time I am not taking the dot product with the unit tangent vector, rather I am taking the dot product with the unit normal vector instead of unit tangent vector, and that is sometimes known as what is called normal form of the vector line integral of f. Okay. So, that also you can think about. So, you may ask that why you are talking about the unit tangent vector at that point. I can also think about unit normal vector. Yes, you can do that. That also you can make the vector line integral, and that time it is known as what is called the, it is known as the normal form of this vector line integral of capital F. That is the way also you can define it, or you can go ahead with that definitions. Okay. So, this is called the normal form of this vector line integral of capital F. Okay, couple of properties like properties of scalar line integrals. What is that? If I have two vector fields whose common domain contains your smooth directed curve C. So, that means I have two vector fields on some domain D subset of Rn to Rn. D contains my smooth directed curve C. Take two scalars A and B, then it is kind of linearity property. That means A times capital A plus B times capital G, integration vector line integral over C. So, A will come outside, B will come outside, and the integral will split it up. So, that is called linearity property number 1. Number 2, again if I have a vector field whose domain contains the smooth directed curve C, and suppose C, my curve C divided into two directed curves, say C1 and C2, and the direction of C1 and direction of C2 are same as direction of C. If this is the case, then I will say that vector line integral of capital F over C dr, which is nothing but the vector line integral of capital F over C1 plus vector line integral of capital F over C2. So, I mean if C is C1 union C2 and has the same direction as C of C1 and C2, then like the Riemann integration A to B, if I take any middle point C in between, so I mean A to B fx dx, which is nothing but A to C plus C to B. Those similar kind of things also true in the context of vector line integral. This one I already discussed. If I have a capital F is a vector field whose domain contains a smooth curve C, and suppose minus C is the opposite curve of to C, which is traces the same set of points traced by C, but in the reverse direction, that we know. In that case, if I calculate the vector line integral of capital F over minus C, which is nothing but the vector line integral of capital F over C, but you have to hit it with minus 1. Okay. So, now I think let us like in the case of scalar line integral, I said a method to calculate the scalar line integral. Similarly, you will have a method for calculating what is called vector line integral. What is that? So, that is I have written. So, method for calculating vector line integrals. So, how to do that? So, the method for calculating vector line integral is given below. That means there are a couple of steps. If you follow it, you will be able to conclude that okay, that is how one can calculate it. So, what is the step 1? Step 1 first. So, since of course, your directed curve or smooth curve is given, so you need a parameterization. So, write a parametric equations capital R T where T running from A to B of the given curve. So, that means if I give a problem, that means calculate this vector line integral of this capital F over your curve C. So, first what you have to do? You have to first get the parameterizations of your curve C. That is the first step. If its parametric equation is not given. So, first you get the parameterizations, number 1. What is the step 2? So, once you have the parameterization, then you can you can have the derivative of r prime t. That means you can easily calculate what is called r prime of t. That is a step 2. What is my step 3? Once I have r of t and capital F is given, then you compute capital F of r of t. So, that you have to do. And now, by the definitions, you have to evaluate this vector line integral of capital F. And what is the definition? Just take capital F of r t dot product with r prime t and then integrate over A to B. So, this step 1, step 2, step 3, step 4, if you follow, I think you will be able to calculate your vector line integral. One example I think I have given. Okay. Yes, for example, I have one example I have given. What is that? So, this is your vector field. If you remember what is that vector field, this is rotational vector field, right. Capital F of x, which is minus y times I cap plus x times j cap, where capital X is the vector x comma y. Now look, I am saying that let C be the upper semicircle of radius 3 with center at the origin and directed from the point P1 to the point P2. So, this time I am just describing what is my curve. I have not given what is the parametric form. Okay, that I have not given. I am saying that okay, it is a upper semicircle. So, if you draw a picture, upper semicircle with radius 3, and what is the starting point? Starting point is 3 comma 0, and what is the end point? This is minus 3 comma 0, right. So, these 2 points. So, that means actually I am talking about this is the corresponding curve C. Okay. Now, you can get the parametric form because it is a circle, upper semicircle, that is on the upper half. Of course, though it is I am in very bad in picture, it is not exactly the circle, it will be more. Anyway, so just believe me that this is a circle. So, what is that? So, what is the equation of the circle? What is the parametric form? Cosine t. So, that means it should be 3 cosine t comma 3 sine t. Okay. But since I am talking about the upper semicircle, so that means this time t will vary from 0 to pi. That is the corresponding parameterizations of this one. So, this is the corresponding parametric form. So, first the step 1, write the parametric equations of C. Now, C is given, which is a semicircle starting from the point 3 comma 0 ending at the point minus 3 comma 0 and with center at origin and radius is 3, then this is the corresponding parametric form. That means, in terms of component it is 3 cosine t comma 3 sine t, but you have to be careful this time t running from 0 to pi, not 0 to 2 pi, because I am talking about only upper part, upper semicircle. Okay. So, now if t is equal to 0, r of 0 is P1, that means if put t is equal to 0, so that means if this component will vanish, so only 3 will be there, that means 3 comma 0 your starting point, and if I put t is equal to pi, that means 3 cos pi, that means this is minus 3 and sin pi will be 0, so that means this is minus 3 comma 0, that is P2. So, therefore, so this is the corresponding parametric form of my curve, and the curve C is directed and oriented from P1 to P2. So, that is the natural orientations anti-clockwise. So, according to these parameterizations, I will have a natural orientation which is nothing but these orientations. Okay. So, step 1 is done. So, that means the way I have described my curve C, then the corresponding parameterization is this is the one. So, first part is done. Now, once I have capital R of t, then what is my next step? Take the derivative of r of t, and r of t is the component. What is my r of t? This is 3 cosine t comma 3 sine t. Now, this component, these are very nice components, sine function, cosine functions, infinitely many times differentiable. So, derivative will exist. So, what is my second step? Calculate what is called r prime t. What is my r prime t? Just calculate the derivative. So, that means minus 3 sine t plus 3 cosine t. So, minus 3 sine t plus 3 cos t. So, that means r prime of t in terms of component, this is minus 3 sine t comma 3 cosine t. Okay. So, this is step 2 is done. What is step of 3? So, step 3 is nothing but f of capital R t. Now, R t is component is given, that means this is 3 cosine t comma 3 sine t, and capital F is also given. What is my capital F? This is nothing but minus y comma x, right. So, you just do it. So, f of x plus x I cap plus y j cap is minus I cap plus x j cap. If I do the calculations, capital F of R t, which is nothing but, so y should be, so this is the y component. So, what is my R t? R t is actually 3 cosine t comma 3 sine t. This is y component. So, that means with minus sign. So, minus 3 sine t plus x component, that means 3 cos t. So, this is the corresponding f of R t. So, step 3 is done, and the last one, what is the formula? That means integration t running from 0 to pi. So, that means 0 to pi. So, that means the vector line integral of capital F over C, which is t running from 0 to pi, f of R t, which is already there, r prime of t, which is already there, take the dot product and perform the integrations. So, that means I have to take the dot product of this times this, and what is the dot product? 3 3, that means 9 sine square t plus 9 cosine square t. Use the trigonometric formula, sine square t plus cosine square t is equal to 1, 9 will come out, this is the corresponding value. Okay. So, very simple. So, that means of course, I am discussing the simple example, that is why, but sometimes if I give some problem, you just have to follow these steps and you will be able to calculate your what is called required vector line integral. Okay. Now, nice applications, what is that? So, let us suppose you have a curve C, suppose this is R t is the corresponding parameterizations of my piecewise smooth directed curve, and let capital F be a vector field whose of course domain contains your curve C. Then the formula that net work done by the force capital F on a particle P by moving P from R A to R B along the curve C can be defined as the vector line integral this is the one. So that you can interpret the vector line integral of capital F over C. You can interpret. Suppose C has a parameterization R of t, and suppose you have a vector field whose domain contains the curve C. Then you can think about the vector line integral is nothing but the net work done by the force capital F on a particle P by moving from the point R A to R B along the curve C. Okay, that is one. In fluid dynamics, what is there? So in a fluid flow, the velocity v vector at each point can be represented as a vector field, okay, at each point the velocity, and the mass flow m vector at each point can be represented as a vector field. Then the corresponding vector line integral, that is v cap over C dr, is called the circulations along C of the flow. So that's the kind of another what is called significance of your vector line integral. So that means if I have a fluid flow, if I have the velocity vector v cap at each point, that can be represented as a vector field, and the mass flow m cap at each point, that also represented as a vector field, then the corresponding vector line integral of v cap over C is actually called the circulations along C of the flow. Okay, so there is another application that is called work done. So what is the definitions of work done? So the work done by a force capital F on a particle traversing an oriented path C is the line integral, okay, or is the vector line integral. That means you have the force capital F, which is a vector field, you have the oriented path C is given, the vector line integral, that is nothing but the work done, that's I am written at work. Okay, there is a small, so that one I already discussed in my last slide. So that is the one. So this is the one. Okay. Now there is a small remark. It says that the total work done by capital F on a particle traversing the path gamma and then reversing back to the initial point. That means suppose this is my gamma. So I am going from here to there and then I am coming back in the same point. So that means the total work done by your force capital F on a particle traversing the path gamma. So that means this is my path gamma. Okay, this is gamma. I am starting from here and going there, okay, and then you see reversing back to the initial point, then actually I am going there and then I am coming back to here. If this is the case, then your work done should be 0. And how do I do that? It's very kind of easy. Why? Path gamma, I think this should be C, okay, this should be C, yeah. So what is my work done? So that means I am going through the curve, so from one point to another point and then coming back, okay. So for going, if I have the curve C, okay, so what is the coming back? It should be the negative of this C. That means for C I am starting with this point, ending that point, and for minus C means what? I am starting with this point and coming back to this point. Okay. So therefore, what is my work done? That means first you have to calculate the vector line integral of capital F over C, and then plus you have to calculate vector line integral of capital F over minus C, right? So that means I am in a path gamma or C, I am going from one point, so this point, to the end point of this curve, right, C or gamma, whatever it is, and then I am coming back. So that means the total work done is nothing but vector line integral of capital F over C plus vector line integral of capital F over minus C. But you know that vector line integral of capital F over negative of this curve is nothing but minus of vector line integral of capital F over C. So that's the formula I have written. So this is same as it is, and this will turns out actually minus of integration over C f dr, and which turns out to be 0. So therefore, if I go and come back, that means total work done is 0. So that is a small remark. Okay, so now I have another kind of way you can think about what is called. I already talked about like path independent in my I think in my last lectures I talked about. In fact, when I talked about this path independence, when I talked about the notions of vector field, then there are a couple of equivalents, if you remember, gradient vector field, path independence. So these are the things I have. Similar kind of things. So it's the path independence implies gradient vector field. What is gradient vector field? A vector field capital F is called the gradient vector field if I have a scalar field F, and if I take the gradient of this scalar field which exactly equal to your vector field. You started with that. There's those kind of vector field is called gradient vector field. Okay. Let's start with the definition. So a subset U subset of Rn is said to be path connected. What is the definition of path connected? It says that if I take any 2 points x and y in my domain U, if there is a path means it's a continuous functions from your closed interval AB to Rn. In Rn I am talking about the path such that the initial point will be x and final point would be y, and not only that, the image of gamma of this interval should fully contain in U. So for example, one simple example I am giving. So that means this is my suppose domain U in R2, take any 2 points. So this is x, this is y. That means for any 2 points x and y there is a path. So that means if I take this path starting from there to there. So, yes, so this is the initial point is x, final point is y, and whole path is contained in U. If this is the case, then I am saying that domain is a path connected. So, a subset U is said to be path connected. If I take any 2 points x, y in that domain U, there exists a path joining from x to y, and that path should lies entirely in my U. And what is the definition of path? It is a continuous function from closed interval a b to Rn, because I am talking about the path in Rn. Okay. If this is the case, so that means if I take 2 points x, y in U, if there exists a path whose initial point is x and final point is capital Y, and that path lies entirely in U, then I am saying that this set is path connected. Then for any 2 points it should happen. Once I have that notions of path connectedness, then I can talk about the first fundamental theorem of my line integral, scalar line integral. What is that? It says that, okay, let U subset of Rn be an open path connected, open set you know, path connected I have just defined. Let capital F be a continuous vector field defined on U. Then the corresponding vector line integral capital F over the path gamma, and that path is very nice. I am saying that this path actually C1 path. That means, of course, path means it's a function, it has a parameterization, and that parametric form it's actually C1. That means it is differentiable and derivative is continuous. Suppose if this is the case, then so what are the things? So that means you have to start with a open and path connected set. Let capital E be a continuous vector field, that means it is a vector field which is continuous. Then the corresponding vector line integral is independent of any path gamma which is C1. That means whatever C1 path gamma I am taking in U, this is the vector line integral is independent, then it will give the same value. If this is the case, then I am saying what is my conclusion? Then there exists a C1 scalar field f, small f, such that you can write your capital F as the gradient of small f. That means then your vector field becomes gradient vector field. So this is very nice. So that means it says that you start with a very nice domain which is open and path connected. Okay, you start with a continuous vector field capital F. Okay, and suppose your vector line integral is independent of any C1 path inside U. That means the value of capital F dr over any gamma I am taking which is C1, if that is the case, then you can have the existence of one scalar field small f from U to R such that capital F becomes gradient of small f. In other words, capital F is a gradient vector field. So that means what? That means once your vector line integral is independent of your C1 path gamma, then means somehow I try to define some kind of indefinite integral, and if I take the derivative I should get back my capital F. So that's the kind of idea, and it is this is indeed the case. So what I am doing, so I am starting with a fixed point x naught. I am defining a function small f from U to R. What is this? F of capital X, which is nothing but x naught to x f dr. Now this is I can define. Why? Because you see I have a say domain U, I have a point x naught and I have a point x, right? Now what is the meaning of this one? Because in x naught and x these are 2 points in higher dimension, there is no ordering, right? So what is the meaning of that? This is a symbol. Meaning is that actually this is same as integration over gamma f dr. And what is my gamma? Gamma is nothing but the C1 curve or some nice curve joining the point x naught and end point is x. Okay, that is the meaning of gamma. Now you can say that, okay, I am not interested in gamma, so suppose this is my gamma, so you can say that I can take this path, another path, gamma 1, let it be, this is the path. But what is the hypothesis? Hypothesis is that this is independent of any gamma C1. That means whether I am taking gamma or gamma 1, this is same as integration over gamma 1 capital F dr joining x naught and end point is x. So that means whatever gamma I can take whose starting point is x naught and end point is x, this is same because it is independent of your gamma. So therefore I can make sense of this x naught to x f dr, and that will give you a function small f of x, that one can check that. So that of course that's I have written where the integral taken over C1 any C1 path gamma joining x naught to x, and of course this makes sense because whatever gamma I can take, as long as x naught is the initial point and x is the final point, this value whatever gamma I will take, all vector line integral over this gamma will be same. So therefore this makes sense, and this small f is well defined. One can check that f is also a C1, and if I take the gradient of this small f, it turns out that it should be exactly equal to capital F. Okay. So that's the kind of first fundamental theorem. If you remember in the Riemann integration, if you have nice function f, then if I integrate a to x f t dt, and if I define as capital F of x, then the derivative of capital F, which is nothing but small f. So this is exactly the kind of fundamental theorem in the context of line integral or vector line integral. Okay. So, that means if I have a nice domain, if I have a vector field, continuous vector field, and if I assume that the line integral is independent of your C1 path gamma, then there will be an existence of a scalar field such that if I take the gradient of the scalar field, it is exactly equal to capital F. That means your vector field becomes a gradient vector field. So, that is I am writing as first fundamental theorem, but just checking is that F is C1 and F is capital F is gradient of small f, that is the part you have to work it out. Okay. So, F is well defined, it is perfectly alright because your vector line integral is independent of your C1 path gamma joining x naught and endpoint is x. That part is perfectly alright, F is well defined. But to check that F is C1 and capital F is nothing but gradient of small f, that is the part you have to work out, and that is I am just leaving it an exercise to you. This is another one. So, okay, this is the second fundamental theorem of my line integrals. Now, what is the second fundamental theorem? If you remember in Riemann integrations, if I have a nice function f and if I integrate my f prime, small f prime over a to b, what is that? This is fb minus fa. That means value of f at the right hand point b minus value of f at the left. So, this is kind of things you can also in the context of vector line integral. What is that? So, that denoted as a theorem. So, let u be a subset of Rn which is open. Start with a scalar field f which is C1, okay, that means derivative exists and derivative is continuous. Okay. So, now let R be a any C1 kind of path in Rn, this is the corresponding parameterizations capital R. So, it is a map from closed interval AB to Rn which is C1 such that range of R of this closed interval AB in U. In other words, actually inside U, you will have a nice curve C whose parameterization is capital R and capital R is C1. Okay. Then what it turns out is that if I do the vector line integral of this gradient of, so f is a scalar field, if I take the gradient it will be a vector field. So, now if I want to integrate of my vector field over C, C means this is the corresponding parameterizations, then it turns out that this is nothing but f of, so R is a parameterization. What is the starting point? Starting point is R of capital R of A and ending point is capital R of B. So, that means it actually value of f at Rb minus value of f at Ra. So, that means whatever path I can take, whatever parameterizations, the right hand side always value of f at Rb minus value of f at Ra. That means it is independent of choice of your path gamma joining Ra end at Rb. Okay. There is a simple proof I have given. So, this is the vector line integral, just the formula. What is the formula of vector line integral? So, this is your capital F. So, this is my capital F. So, that means what you have to do? You have to just take the capital F of Rt dot R prime t dt and parameterization is given a to b. So, that is perfectly alright. So, that is the exact definitions of your vector line integral of capital F which is nothing but gradient of small f, right? This is there. So, now what is this? This is very nice. So, look, what is R? R prime of t, it is a vector in what? R prime of t is a vector in Rn, okay, and what is gradient of f at Rt? That is also a vector in Rn, okay. So, now if I take the dot product, it will be a scalar and which is nothing but actually the derivative of these functions, because you see if I take the composition function f composed R, it is a map from where to where? It is a map from A to B to what is this? To R. Okay, because R is a function which maps AB to Rn, okay, and this is a curve and small f is defined on U which contains my R of AB. So, therefore, this composition makes sense, that means f of Rt makes sense because range of R which is actually domain of f, that is why R of AB contained in U and f is defined on U. So, this makes sense. So, therefore, these are functions from R to R. What we have to do? You have to just have the chain rule. So, what is the chain rule? d dt of f composed R which is nothing but what? Derivative of f at the point Rt which is nothing but gradient of f at the point Rt dot product with R prime of t. This is the chain rule, right? So, this is by chain rule you can write d dt of f of Rt, and now you apply the fundamental theorem in the what is called in the single variable case. So, what is this? This is nothing but you can write it, this is a to b f composed R prime t dt and which is nothing but f of f composed R at b minus f composed R at A and which is nothing but this one, because I am using this formula. Because this time f prime, what is my f prime? Here my f is nothing but f composed with R. It is a functions from R to R, okay, and I am talking about the integrations a to b, the derivative and times dt. What is this? This is nothing but value of f composed R at the point b minus value of f composed R at the point A, which is nothing but f of Rb minus f of Ra. So, that means the gradient field, that means I am taking the vector line integral of this gradient of small f, that means the vector field, right, gradient vector field. the gradient vector field implies the path independence. Yes, of course, it is path independence, because the right hand side value depends only at the initial point and at the final point. That means initial point is r of a and final point is r of b, and the value of this vector line integral on any path C joining the point R A to R B, which is nothing but the right hand side f of R B minus f of R A. So, that means only the initial point and final point value will determine the value of the vector line integral. Whatever path I can take, joining point is R A and end point is R A, that means it is nothing but the what is called path independence. Okay. So, this is I am stating this is a second fundamental theorem, because just to kind of have some comparisons with the second fundamental theorem with that one, and first one is that capital F prime x is nothing but small x. So, this kind of things. So, this is in the R to R functions. Okay. Okay. So, R to R function is if I have a functions from R to R, and if I define capital F x, which is nothing but a 2 x f t dt, and then derivative of capital F is nothing but small f. So, this is sometimes I am saying that is a first fundamental theorem, and this is the corresponding generalizations as a line integral, first fundamental theorem, and second one is that integrations of f prime f b minus f a, and this is the corresponding generalizations of this second fundamental theorem in the context of multivariable setting. Okay. So, I think I am done with this what is called this scalar line integral and vector line integral. So, I just discussed in last 2-3 lectures the notions of scalar line integral, notion of vector line integral, couple of properties, and then couple of examples I have calculated explicitly. And of course, to talk about this scalar line integral and vector line integral, I need the notions of what is called curve, smooth curve, piecewise smooth curve. Those are the things I have discussed. So, that is very brief about scalar line integral and vector line integral. In my next lecture, I will talk about I think surface integral or this kind of concept, because anyway at the end of my lecture I want to talk about what is called Stokes theorem and Green's theorem. So, in my next lecture I will talk about something new, that means I think surface integral, those kind of things I will start discussing. I think I should stop here, because this is the end of your what is called scalar line integral and vector line integral. In my next lecture I will start with something new. And of course, at the end I will talk about, of course, it needs couple of lectures, because in my last I think last 2 weeks I think I need to talk about what is called Stokes theorem and Green's theorem. So, to talk about Stokes theorem and Green's theorem, I need to develop something. Okay. So, and that I think discuss in my next lecture. So, I think I should stop. Thank you.